Welcome back. In this segment, we're going to use recurrence relations to model problems and to solve problems, in particular counting problems. Now remember, in a previous lecture, we solved counting problems like determine the total number of bit strings that either start with a given pattern or end in another pattern. Now these problems were relatively easy, and we were able to solve those using the three basic counting rules. Now there are problems that are a little bit more complicated that require more sophisticated techniques. And so in this segment, we're just going to show a couple examples of how to apply recurrence relations to solve some of these bit string counting problems. Now, of course, recurrence relations can be used to solve a multitude of different problems. So here is the problem we're going to look at. Count the number of bit strings that do not contain the substring 00. So notice these problems are a little bit more complicated. First of all, we want the pattern to not appear in the string, which is the complement of the kind of questions we asked before. Second, the pattern is not limited to the beginning or the end of the string. Okay, we don't want it anywhere in the string. And third, we're not limited to bit strings of length 9, say. We want a general formula for any bit string with this property of any length n. So for that, we're going to use the notation a sub n to denote the number of strings with this property that have length n, where n is greater than or equal to 0. So to make sure we agree on what a sub n denotes, let's look at a couple of simple examples. So what is a sub 0? Well, by definition, a sub 0 is the total number of strings of length 0 that have this property. Well, it's easy in this case to answer this question. We can just enumerate the strings of length 0. There's only one, it's the empty string. And does this string satisfy this property? Sure it does. It does not contain a 00 since it doesn't contain any character. So the total number of strings of length 0 that satisfy this property is 1. Now how about a sub 1? Well, again, there are two strings of length 1, and neither one of them contains the substring 00. So the answer is a sub 1 is equal to 2. Now you see, you could keep going like this and compute the next terms in the sequence, but eventually it's going to become hard to do. When n becomes large in a sub n, you don't want to have to enumerate all of the strings of that length to figure out how many of them satisfy this constraint. So instead, what we want as a solution is a formula for a sub n. And so the technique we're going to use now is going to be able to find out what recurrence relation must be satisfied by this sequence a sub n. So let's try to come up with a formula for a sub n. Now remember, a sub n is the number of strings of length n that satisfy this property. Well, it's not obvious how to come up with a formula, so we can break down the problem into two cases. There are two kinds of strings with that property, those that start with 0 and those that start with 1. So we can use the sum rule and add up those two numbers once we have computed them. So I'm going to write this expression like this. This pound sign here with parentheses means the total number of strings that satisfy this property and that have this form. And here what I mean is that it's the strings that start with 0 and then have anything after that. Now, as I said, the strings that have this property either start with 0, so they have this form, or they start with 1, so they have this form. And because those two sets of strings do not overlap, we can use the sum rule. So let's read this in English. The total number of strings of length n that satisfy this constraint is the sum of the total number of strings of size n that start with 0 and that have this property, plus the total number of strings of length n that start with 1 n also have this property. That's just the sum rule. So now let's compute these two numbers. First, we're going to leave this expression unchanged and we're going to focus our attention on this number. This is the total number of strings of length n that start with 1 and do not contain the substring 00. So another way of describing this number is the total number of strings that start with 1 and end with any string of length n minus 1 that does not contain a 00. So how many such strings are there? Well, because the 1 here has no chance of participating in a 00 pattern, we can pretty much ignore it because the total number of these strings is the same as the number of strings of length n minus 1 that do not contain a 00. And that number, even though we don't know its value, we have a name for it. It's a sub n minus 1. Remember, by definition, here, a sub n minus 1 is the number of strings of length n minus 1 that do not contain a 00. And that's exactly the same number of strings as this term. So here we see the beginning of a recurrence relation where a sub n is defined as a function of the previous term in the sequence a sub n minus 1. But to complete the recurrence relation, we need to compute this number. So let's focus our attention on this number. Now notice we have a substring of length n minus 1, just like here. So I want you to pause the video and think about whether the value of this number should also be a sub n minus 1, just like we did for this expression. Okay, so hopefully you came up with a negative answer to that question. Here is why. Consider, for example, the string of length n minus 1 that has a 0 and then all ones all the way to the end. That string is definitely counted in a sub n minus 1, right? Because it does not contain a 00. However, it should not be counted in this number. Why? Because even though it only has a 0 and then all 1, so it doesn't contain a 00, once you stick a 0 in front of it, the resulting string has a 00 in the front and therefore should not be counted in this number. So because of this leading 0 here, we cannot use the same reasoning to infer that this number is a sub n minus 1. In fact, I can't think of a direct way of computing this number, so instead let's use the same trick we used over here and let's divide this set of strings into two sets. Those that start with 0, 0 and those that start with 0, 1. In other words, let's focus on this position here, which can either be a 0 or a 1. Well, here things become easier because we can't have a 0 here. So all the strings that start with a 00 are eliminated. So we know that the number of strings we're considering here then must always have a 1 in its position. In other words, this number must be equal to that number. And what is that number? It's the number of all strings that start with 0, 1 and then are followed by a substring of length what? Well, n minus 2, since we removed one more bit. And this substring may not contain a 00. Well, we don't know what this number is, but we have a name for it. That's a sub n minus 2. Remember, here we can apply the reasoning that we applied for this term because we have a 1 just preceding the substring. So there is no way this 1 could become part of a 00 pattern even if you add just a single 0 in the front here. So this term is equal to a sub n minus 2, and let's not forget to add the a sub n minus 1, and now we have a final answer, a final recurrence relation for this number And that recurrence relation is a sub n equals a sub n minus 2 plus a sub n minus 1, which means it's basically the recurrence relation that is satisfied by the Fibonacci sequence. So now you could compute a sub 2 very easily. It's just 2 plus 1. So a sub 2 is 3, and a sub 3 is 5, and a sub 4 is 8, and so on and so forth. So in other words, we used recurrence relations to solve this slightly more complicated counting problem. Now let me give you a second similar problem as a practice problem. I want you to count the number of bit strings that do not contain the substring 111. So as before, we're going to approach this problem with a recurrence relation. We're going to call the generic term in that sequence a sub n, with the same meaning as before. You can always compute the first couple terms for the same reason as before. A sub 0 is 1, a sub 1 is 2. And again, you don't want to keep computing those terms by just counting the total number of strings and then counting how many out of those satisfy the constraint. You want to get a formula that allows you easily to compute the next term and the next term and so on and so forth. So really what we want is a recurrence relation, and since we don't know how to compute a sub n, we're going to split that number into the sum of two numbers, namely the sum of those strings that start with 0 and those that start with 1, same as up here. And let's focus our attention on this first number. Well, notice these strings start with 0. This 0 cannot be a part of the 111 pattern. Therefore, the total number of strings of this form is nothing but the total number of strings of length n minus 1 that do not contain a 111 pattern. And that number is just a sub n minus 1. Now, when we turn our attention to the second number, we can't use that approach again because this one could be the beginning of a 111 pattern. So this number, and make sure you're convinced of that, is not a sub n minus 1. So since we don't know any better, we're going to split this set of strings into two non-overlapping sets of strings, and using the sum rule, we can transform it into this addition of all the strings that have this pattern and that start with 1, 0, plus all the same strings with the same pattern except they start with 1, 1. Now, how many strings of this kind are there? Well, we have n minus 2 bits left, and since this 0 cannot participate in the 111 pattern, this number is nothing but a sub n minus 2. Now this number, we may not be able to compute it right away, but one thing we know is that if a string starts with a double 1, it cannot be followed by a 1 because otherwise it would break our constraint here. So we know that this number is also equal to the set of strings that start with 1, 1, 0. So let me write it down. And now we can probably compute this number more easily because notice we have a 0 here, and this 0 cannot participate in the 111 pattern. Therefore, this number is equal to what? It's equal to the total number of strings of length, whatever that is. Well, that's n minus 3. So it's the total number of strings of length n minus 3 that do not contain the 111 pattern. And that number is a sub n minus 3. So there we have it. You have a sub n is equal to this sum of the three previous terms, and that's our recurrence relation. Now, one problem here is that because we're using the three previous terms, the initial conditions that we computed up here are insufficient because we only computed the first two terms. So we're going to have to compute the third term, and together the first three terms plus this recurrence relation will completely define the solution. So let's compute A sub 2. It's the total number of strings of length 2 that do not contain triple 1. Well, that computation is easy. There are how many strings of length 2? Well, the answer is 4, and neither one of them obviously contain this pattern, so A sub 2 is 4. Now that we have this recurrence relation, we can easily compute the value of the next few terms. So for example, A sub 3 is 7, because 7 is equal to 4 plus 2 plus 1. Now in this case, we can check our work because how many strings of length 3 are there? There are 8 of them, and only one of them contains 1, 1, 1. So here are the 7 strings that satisfy our constraint. Now how about A sub 4? Well, A sub 4 is simply enough 7 plus 4 plus 2, that's 13. Now let's quickly illustrate the way to build those 13 strings. First, you start with the 7 strings of length 3, here they are, and to build a string of length 4 that does not contain a triple 1, you just add a 0 in front of all of those. Then you look at all the strings of length 2. There are 4 of them. Here they are. And from those, you can get a string of length 4 again that does not contain a triple 1 by adding 1, 0 in front of them. And finally, you look at the strings of length 1. There are 2 of them. And to get a string of length 4 that does not contain a triple 1, you just add 1, 1, 0 in front of them. And so 7 plus 4 plus 2 gives you 13. Now again, this is just for illustration purposes. We don't need to do any of this string counting to get the answer. So let me show you that. Let's compute A sub 5. Well, A sub 5 is just 13 plus 7 plus 4. That's 24. Let's do one more just for fun. A sub 6 will be 24 plus 13 plus 7, and that's 44. So in conclusion, we were able to derive a recurrence relation to solve this counting problem, which is much easier than actually listing all the strings and counting them. Now, it's not quite as good as having a closed form formula because you have to compute the terms one by one, but it's still a pretty nice solution to this problem.